Okay, so what we need to talk about today is how to find a confidence interval for population mean. So first thing to remind you of, the reason you do a confidence interval is because you don't know the population parameter. So before, we didn't know P, we didn't know the population proportion of something. Now, we don't know the population mean. There are two different formulas, though, for a confidence interval for mean, depending on whether or not you have the population standard deviation, which is sigma. If we don't have the population mean, do you think we're going to have the population standard deviation? Probably not. So 99.9% of the time, you do not know the population standard deviation. That is the vast majority of the time. Okay, so confidence interval formula, you start with a point estimate. So that'll be X bar. Sample mean we use to estimate population mean. And then it's going to be plus or minus. And then we have our margin of error. With proportion, we used Z and then standard deviation. Here we use T and the standard deviation of the sampling distribution, which is S over root N. Now, here's what changes. If we do know the population standard deviation, that S is going to be a sigma, and instead of T, we use a Z. Otherwise, though, everything else stays the same. We still have X bar, and we still divide by root N. I will tell you in all practicality, I have never seen this formula on the left actually used, because we never know the population standard deviation. So theoretically, on the AP test, could you be given an example where you need to use Z? Yes, theoretically. But the vast majority of the time, you should be using T. Here's what you need to know. T is based on degrees of freedom. And that's the table we've been looking at. Table B is the T table. And then just some things we talked about before. Everything after the plus or minus is called the margin of error. What is the other term for margin of error? Nope, but that's an important term also. Bound. So margin of error or bound. If we don't include the T and it's just the S over root N, that is our standard error.
What is standard error?
It is an estimate of the standard deviation of the sampling distribution. The standard deviation of the sampling distribution would be sigma over root N. Because we don't have sigma, we're using S to estimate sigma. Similar idea with proportion. We would need P. We don't have P, so we use P hat to estimate. Okay. Z, if you remember, is the standard normal curve. So that's Z-scores. T is just another type of curve. It's a type of distribution. It's a type of curve. Few things that you need to know about the T distribution. First thing, the T distribution is centered at 0.
Mm-hmm. Standard T1 is 0, 1, 2, 3 as well?
So there's not really a standard T because it's based on degrees of freedom. But
so wouldn't it depend on the sample size?
Yes. Yeah, but it's not like normal where we have like Z-score normal and then all the other normal. There's just T. So the center is never going to change and the spread is based on those degrees of freedom. Aiden?
The degrees of freedom, like the numbers on the left's coming down like to infinity.
Yes. Okay. The T is symmetric, like Z, but more spread out. So the Z distribution, our standard normal distribution, you know that curve. The T distribution is going to be symmetric like that, but it's more spread out. And then this is by far the most important property. As the number of degrees of freedom increases, the T distribution approaches the Z distribution. So as the number of degrees of freedom gets higher and higher and higher, T becomes Z. And that shouldn't shock us, because when we looked up Z for proportion, we used the T table. And if you notice, going down the left side, degrees of freedom are getting bigger until we get to infinity. When we get to infinite degrees of freedom, that's just Z.
What are degrees of freedom?
Oh, such a great question. They're a parameter. I don't have more for you than that. Generally, the way that degrees of freedom are explained is it's the amount of quantities that you can change. So here's an example. If we talk about variance, we have our formula of x minus x bar squared over n minus 1. Okay, so do you remember talking about how we square this because the quantity without squared is 0? So we say that variance has n minus 1 degrees of freedom because those n minus 1 observations can be whatever they want, but then you can figure out the last observation by knowing that the deviation sum to 0. Asking what degrees of freedom is kind of like that math question that nobody has a good answer to. But that is the best answer that I've been given. Okay, so practically, how does this affect us? We're still doing panic. PANIC, all of it stands for the same. What I'm going to write down is the differences. P, still parameter. You're not using P, though, this time. You're using mu. And you would say it's the population mean, blah, blah, blah. A, assumptions. All three of the assumptions are the same. First assumption, always random sample. And we need to be specific, please. Some of you on your quiz just wrote random question mark. No. Random what? Random sample. What is the second assumption? Approximately normal sampling distribution. You have to write sampling distribution. That's another thing people did on their quiz. They wrote approximately normal question mark. That's not sufficient. Now, this is what makes mean harder than proportion. Question, comment?
Can you just write large sample?
No. And here's why. For proportion, you can. The question was, can you write large sample? Proportion, you can. Mean, you can't. Because there's more than one way to check this. Okay. There are 3 different ways to check that you have an approximately normal sampling distribution. The first way is you're told the population is normal. If the population is normal, you're done. The sampling distribution will be normal. If the population, you're not told anything about the population, what's the other way?
Greater than or equal to 10.
Not 10.
Greater than 30.
Greater than 30. What is that called?
CLT.
Central limit theorem. Okay. Sometimes you will not be told either of those. So your last resort is that the sample does not show extreme skewness or outliers.
Is that saying within the sample or is that part of the calculation?
The sample itself. So you would have the raw sample.
And you calculate outliers from the sample data.
Well, we're going to do an example. What you're going to do is you're going to graph the sample. But you're not going to graph it by hand, you're just going to use the calculator. Okay, and then third assumption, 10% rule. But remember, that's only if you're sampling without replacement rather, from a finite population. For n, this is a one sample confidence interval for mean. That was something some of you forgot on the quiz. You just said one sample confidence interval. You have to tell me it's for mean. You're using t, and you have n minus 1 degrees of freedom. So that might be easy to forget. When you use z, there's no degrees of freedom. But with t, you have to include degrees of freedom. And then, of course, you're going to give the percent. Priyanka?
For the third assumption,
Yep.
if it says specifically that it's without replacement and we still do it, would that take points off?
No. If it says with replacement, you don't have to. So if it specifically said, yeah, we sampled with replacement and you did it anyway, there. Okay, C is the same. You're still going to have your two sentences. For the interval, we wrote it above, x bar plus or minus t times s over root n. Of course, theoretically, it could be x bar plus or minus z times sigma over root n. Like I said, though, I've not seen an example where that's actually used because we pretty much never know the population standard deviation.
Does the central limit theorem apply if n is equal to 30?
I would apply it, yes. I don't think you'll ever get one where n is 30. It'll very clearly be above or below. Okay, we are going to do, Priyanka.
So if it's not 30, we just would stop the problem there?
Okay, so students always ask me this. What happens if I'm checking the assumption and one assumption is not met? If you are asked to carry out the confidence interval, like it says construct a confidence interval, and one of the assumptions is not met, carry the whole thing out. But then in your conclusion, you're going to write, one of the assumptions was not met, so I question this interval. If it says, are the assumptions met, yes or no, as soon as you see one that's not met, you're done. Okay, we are only going to do one panic together. That's it for mean, and then you're not going to do any more examples besides your homework. So you might want to pay pretty good attention. But we're going to do the one on the next page. If you don't have a calculator out, please take the calculator out. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output reading in millivolts. Some variation is inherent in the production process. Below are tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension of all the screens produced on this day. Okay. Key word, first of all, is mean. So that tells us we're using mu and not p. Okay, so we are going to let mu be the population mean. Don't forget the word population. Tension of all screens produced on this day. First assumption, is this a random sample? Again, please make sure you put the word sample. It says from a random sample. So we're going to say stated. Next, we want to know, do we have an approximately normal? Sampling distribution. Okay, so again, there's three ways to check it. First, we could be told the population is normal. We're not. Second, we could use the central limit theorem, which we can't here because there's only 20 observations. So we're gonna have to look at the sample. So right now what I want you to do is please enter all 20 of these numbers in a list. Okay, so we need to look at a graph of the sample. So did we go to stat plot? And did we turn the first plot on?
Yeah.
Okay, so you have two options here to show skewness or outliers. You could either graph a histogram, which is the first row, the last one, or you can do a modified box plot. I'm going to do a modified box plot. Then make sure that you have the right X list. My X list is L1. And then when you're ready, you're going to hit zoom 9.
You're not supposed to.
But there should not be a Y list because you're graphing a box plot which only has one list.
Which graph should we use? Zoom 9?
Which box plot?
Which graph? There's two box plots.
You're going to use the one that has a dot because that will show outliers. The other one does not show outliers.
So my calculation. What is this?
Mine's pretty one.
And what button do you click when you're on?
Asymmetric? Yep.
What button do you click?
Zoom 9 because it'll reset the window.
No frequencies.
At this point, we are going to draw that graph and write a sentence about it. So just sketch it. You don't need to label anything. What you are looking for is there any outliers or is there extreme skewness? Which there's not. I'm going to be very picky about this sentence. Because the sample, that's the one that people mess up, because the sample does not show extreme skewness or outliers, the sampling distribution is approximately normal. So you need to be very clear that this graph is a sample, which tells us that the sampling distribution is approximately normal. Do not draw a graph unless you have to. So if you can use the central limit theorem, use the central limit theorem.
What would our sentence be for if it was a central limit theorem?
You can just say yes by the central limit theorem. What I would do is whatever your sample size is, show that it's bigger than 30.
Couldn't you have well, like you have a non-normal one, even if you get a sample that's normal, like a non-normal sampling distribution, because there's and if you were to take a different sample, you get a bunch of outliers. So potentially, just because one sample shows
Yeah,
normality.
that's not going to be a concern of ours, but theoretically that's possible, yes. Aiden?
Do you have to go through and say and it's not bigger than 30?
No.
Okay.
No. The only other one that people mess up is if the population's normal. Sometimes people will say approximately normal sampling distribution. Yes, it's stated. That I will take off for. It will never be stated that the sampling distribution is normal. The population will be normal. Okay, third one, sample size has to be less than 10% of the population size. I don't know how many of these screens are produced, so we're just going to say we will assume more than 200 screens are produced each day. Really, it should be this day. Now we're ready for N. We only have one sample, not two, so it's a one sample confidence interval for mean. We have 90% confidence. And we are using, okay, so this is where we have to decide if it's T or Z. We've not been given a standard deviation. We have a sample though, so we will be using the sample standard deviation once we calculate it. That means that we're using T, and we have to include degrees of freedom. It is always n minus 1. So in this case, that's 19. You do not have to show 20 minus 1. I'm just showing it so that you have it in your notes. Okay, formula, we have x bar plus or minus t times s over root n. Okay, this is a little more tedious than proportion. X bar you have to calculate, s you have to calculate. You don't have to show work, your calculation will do it for you. So just go back and do the 1 var stats. Sample mean is 306.32. I'm going to leave a space for t. S is about 36.209 over the square root of 20. T, you're going to find on the table. So keeping in mind, degrees of freedom is on the left side. You're going to go to 19 degrees of freedom and then go over to 90%. So 19 degrees of freedom, 90% confidence is 1.729. Okay, so then let's calculate this real quick. This is the confidence interval I get, 292.32, 320.32. You guys agree? Okay, questions before we write our conclusion?
Can we also check this, how we check the population proportion on the calculator?
Yes, once we write our conclusion, we'll talk about that. Okay. Just for fun, let's write a conclusion. Then we're going to talk a little bit more. I am 90% confident that the population mean tension for all screens produced on this day is between 292.32 and 320.32 millivolts. It's mean, so include units. Then we have to interpret what that 90% actually means. So 90% means, in the long run, in repeated samplings of size 20, approximately 90% of intervals constructed in this manner will contain the population mean tension blah, blah, blah of all screens produced on this day. this second sentence. You're going to write every single time you do a panic. So some of you I know are not putting a ton of effort into remembering it. I would, because you're going to get points off every time. Okay, quick questions, or quick question for you. If the tension has to be at 330, and I asked, is there evidence that the mean tension is 330? What would you say? No. If the mean tension is supposed to be 320, and I asked you, is there evidence that the mean tension is 320? What would you say?
Not enough.
It's possible.
It's a yes or no question.
Yes, there is evidence,
No.
No.
but not guaranteed.
What do you trust to say?
Okay. Okay. What I want to talk about real quick before we move on. Priyanka asked, is there a way for us to check this on the calculator? There is. Please listen. Some of you think it's not important to know how to check these on the calculator. I will tell you on the AP test, the formula and the work are not required. All that's required is the interval itself. So if you know how to do this on the calculator, you can save yourself a lot of time and mistakes by just doing it on the calculator. You will be learning 6 or 7 different confidence interval formulas and 10 different formulas for the other process. So it's pretty possible that we're going to mess the formulas up. So if we just learn how to do it on the calculator, that's going to be helpful. What I want you to do, I can't show you this, I'm just going to talk through it. If you hit stat and go over to tests, we're not doing a test right now. We are doing an interval. So if you go down to my calculator, it's number 7 and number 8.
Z and T intervals.
Z interval and T interval. Okay, if you remember, for proportion, the calculator will always say proportion. It'll say 1 prop Z interval or 2 prop Z interval. Z interval and T interval, though, are for mean. Z interval, you're very rarely going to use. T interval is the one that you're going to use. So click on T interval, and then you're actually going to notice you have 2 different options. Data versus stats. Data means you have the raw data in the calculator. Stats means you have the summary data. So click stats real quick, and you'll see you'd have to enter X bar and S and N, so on and so forth.
It fills it in for me.
Yeah, this time it's filled in because we put the data in. Go back to data, and you'll notice it's going to say list, frequency, and confidence level. So list is L1, frequency is 1, your confidence level is 0.9. And if you hit calculate, you should end up with the same interval that we got above. You agree?
Yeah.
Okay.
Yes.
The expectation is that you are always checking your answer with the calculator because I promise you it's going to save you time on the AP test. Okay, questions about panic for mean. Okay, quick note for you. Do you notice that all the degrees of freedom are not listed on here? Like if you had a sample size of 35, how many degrees of freedom would you need? 34, not on the table though. So here's what you're going to do. If the degrees of freedom is not on the table, you are going to round down. So instead of 34 degrees of freedom, you would use 30.
But you have like 39 degrees.
Technically, you're supposed to round down. That being said, on the AP test, either one will be accepted, and I would accept either one as well. The reason we round down, it gives us a slightly bigger t value, so it's a conservative confidence interval. Okay. Questions? Let's go to the next page real quick then and just do some rapid fire on these. How would a 99% confidence interval compare to 95%? 99% is wider. Yes, wider, not bigger. How does a larger sample size change the interval?
What's variance?
Yeah, it makes it narrower. Okay, what sample size would be needed to produce a 90% confidence interval with a margin of error of 0.04? So we would have our t, our s over root n. We want it to be less than or equal to 0.04. Now, here is the difficulty. If we don't know the sample size, can we figure out t? No, right? T is based on degrees of freedom, which is based on the sample size. So if you're ever going to do this, in place of t, you have to use the z value because we don't have degrees of freedom. So z for 90% is 1.645. And then you would solve for n. Okay, that's the notes. That's panic for mean.